Mm.
Hi, my name is Amanda Agee,
And my name is Zubin Wadia.
and we are partnering with both Yankee Casting and the Air Force Research Laboratory on improving quality predictors for simulating the solidification of magnesium aerospace castings. So, for some background, Yankee Casting focuses on creating magnesium castings for various automotive and aerospace companies. Currently, they are outsourcing a specific magnesium casting called AZ92, which exhibits unwanted feathery-like microporosity or holes because it's a large freezing range alloy. Therefore, design rules will be evaluated and improved upon in order to meet industry standards so that the casting is radiographically sound after its initial production and to ensure its high strength to weight ratio. The senior capstone design team will then utilize Procast, an advanced casting simulation tool, to evaluate and improve current design rules that Yankee Casting can continue to follow in their foundry in order to streamline their AZ92 casting production. However, due to the current climate of COVID-19, the main goals or objectives of this project have shifted due to the delayed availability of accessing Procast remotely. The newest goals for the academic semester was to investigate AZ91 and develop relationships to AZ92. So with that being said, with our literature review, it was determined that AZ92 is a large freezing range alloy as backed up by image A showcasing a 200-degree temperature range as noted in the pink color. And large freezing range alloys tend to have mushy zones that lead to porosity. And as molten metal is being poured, the liquid portion of the metal has to flow out of this mushy solid plus liquid region in the riser beyond the solid dendrite that exists in the alloy. Therefore, there's a very high resistance to fluid flow that can lead to porosity in this specific casting. And therefore, knowing the cause of porosity, we want to understand where the porosity tends to form. And with this being said, we will transition to using the engineering design process that's backed up by Procast. So seeing that AZ92 is not readily available on Procast and because delays were experienced throughout the time frame of this project, the test casting instead analyzed AZ91 as the main material because a database of the material's properties were readily available in the simulation package. Various simulation kinetics, casting parameters, and alloy parameters were investigated for AZ91 in order to produce different profiles that Zubin will speak to. And these profiles will provide reference to behavior AZ92 should similarly exhibit.
So the graphical data that we collected regarding AZ91 shows that AZ91 undergoes dramatic change over its freezing range in properties such as density, heat conductivity, and of course fraction solid over temperature. Now, in the case of AZ92, these data will likely be similar with a few distinctions due to the differences in things like density and liquidus and solidus points. So the simulated data that we did use was created using a part that replicates many of the pitfalls that are found in sand casting, things like complex shapes, low flow due to shape, as well as thick areas that cool down at a lower rate due to lack of ambient cooling. And these simulated parts are also poured at different initial temperatures to simulate different superheats, which also affect porosity. So these parts, we poured, the one on the left was at 610, the one on the right was at 700. The two purple spots in each sample show where the porosity is tending to concentrate at least 2.3%. Those are prime spots to place something like a chill, a riser, or a sprue to lessen the porosity in those areas. We also use what's known as the Neyaman criterion, and that essentially measures how good the alloy is at a certain point in freezing in one direction. Again, 610 on the left, 700 on the right, and the maximum Neyaman criterion shown is 3. So anything in purple is a prime spot for a chill, a riser, or a sprue to help reduce porosity. So over the semester, we used Procast. We found our porosity sites. So this determines potential locations for chill placement. We studied AZ91 characteristics. So any estimations of risers, sprues, and chills for AZ91 will still be relatively accurate for AZ92 castings. And we used Procast to determine porosity calculations and NEOM criterion, which helped us find where to put various rigging to reduce porosity. So our goals for the next iteration of this project will be to identify different profiles for AZ92 castings.
So with that being said, looking at some final points, we did run into some technical constraints, being that there was limited access to Procast and its availability, as not being able, and as well as we weren't able to transition into the experimental analysis phase of this project, as well as completing the computational analysis in its full entirety. However, looking at our timeline, we're really grateful for the progress that we were able to complete and look forward to seeing the next senior design team complete our project and pick up from where we left off.
We would like to thank Air Force Research Laboratory. We would like to thank Yankee Casting, with special thanks to Kevin, Mark, and Tim Becchiarelli and Holly Hazempa, as well as the University of Connecticut, with special thanks to distinguished Professor Dr. Harold Brody and PhD student Mohammed Diapour.
Thank you.